Hi, Algebra 2 students. In this video, we are going to be doing a review of basically everything that we have done so far with polynomials. And this will be preparing us to take the polynomials quiz. The first thing we're going to talk about is graphing. And I know you have seen this slide before if you've been in class. We've actually gone over it in 2 different classes, but I cannot overstate how important it is to understand what you need to know in order to be able to graph a function, because there may be instances where you are prompted about things like what is the end behavior, what are the zeros, what are the multiplicity, but there will also be times when you just need to look at a function and be able to graph it. So if you're ever asked to graph a function, what you need to be aware of before you can graph are the zeros, which are the x-intercepts. You need to know the end behavior, right? So am I pointed up or down at both the left and right end of the graph? And that can be determined based on whether there's an even or odd degree and positive or negative leading coefficient. And then you need to know the multiplicity. The multiplicity being the number of times a root occurs. So for instance, if you had something like x minus 2 squared, right, because that is occurring twice, it has an exponent of 2, that would be what we'd call even multiplicity. So at the 0 of 2, right, you wouldn't cross the x-axis, you would just bounce off of it. A quick review of the end behavior too, kind of skipped through that. Whenever you have an even degree function, you will have matching end behaviors. So you would have something that maybe it looks like this, where both the left and right side point up, or both the left and right side would point down. And then with an odd degree, you would have opposite end behaviors. So something like this, where you start down and end up, or something like this, where you start up and you end down. Now, you also need to know about the positive or negative leading coefficients. So with a positive leading coefficient, you will have an even function that points up on both sides, or an odd function that is increasing, right? So we're sort of looking in like quadrants now. So this left column, both of those would be positive leading coefficients, right? In this example, we are pointed upwards. In this example, throughout the function, so from left to right, I am increasing. And it's not necessarily that every point you're increasing, but it follows that overall increasing trend because it starts at the bottom and it ends at the top. Whereas the negative leading coefficient, you would see a graph that either points downwards on both ends or one that starts at top and ends down at the bottom when we read it left to right. So with all that being said, let's go into an example of how to graph. This one will be sort of prompting us along the way. We are going to start by finding our zeros. So recall, when I'm looking for my zeros, I'm looking at each factor individually, and I'm saying, what number could I plug in for x to make this factor equal 0? In order to make that factor, x plus 4 equal to 0, x would have to be a negative 4, right? Because negative 4 plus 4 would give me 0. So it's going to be the opposite sign of what is present there. Now, as we reviewed in class, you could, for every factor, always write it out as an equation and set it equal to 0. But we have these memory tricks to save time. So once you know this pattern, once you know, oh, it's always going to be the opposite sign of what's there, because those will cancel, it's faster to do that than to bother solving these equations over and over and finding that way that x is equal to negative 4, right? So we save time where we can save time. So my first 0 was negative 4. Oh, how did I skip pages? Well, oops. Okay, we're back. Sorry about that. So we already found from this factor that 1, 0 would be negative 4. We found from this factor that 1, 0 would be positive 3. And we found from this factor that 1, 0 would be negative 1. The next thing that we are going to have to do is figure out if this is an even or an odd degree. Now, degree, remember, that is the highest exponent. But if we're in factored form, we have to look at the total number of x's being multiplied throughout this entire function. So I'm going to look and say how many x's are going to come from this factor here. So since this expression is squared, there's 2 x's coming from there. Now with this next factor, it's not raised to an exponent at all. So there's just that 1x. It's not being multiplied times itself. 1x comes from that factor. Then the third factor is being raised to the third power, so I would get an x cubed out of that. That's 3 more x's. So in total, if you were to actually expand this function, you would have a term with 6 x's being multiplied, or in other words, that would be x to the 6th. And because of that, this is the 6th degree, which is an even function, an even number. Next thing I'm doing is looking at the leading coefficient. So that's if there is a number being multiplied out in front. If there is no number, it would just be 1. In this case, what do I see? I see a negative sign. Well, there's no number associated with that negative sign, so it's not like it's a -2, a -3. It is simply a -1. So my leading coefficient is going to be negative. What does this tell me? Well, I'm going to have matching end behaviors because of the even degree, and it's going to be pointed down because of the negative. So my function would look something like this. That indicates that both my left and my right end behavior is going to be that the function approaches negative infinity because negative infinity is down at the bottom. Now, I do want to emphasize something before moving on. Remember that it is the degree that we care about being even or odd, and that it is the leading coefficient that we care about being positive or negative, because sometimes people get this mixed up. So the degree determines the end behavior, like whether it's matching or opposite, and the leading coefficient determines if it's basically positive or negative, meaning pointed up or pointed down. Just make sure you don't switch those and like check to see if it's a positive or negative degree and an even or odd leading coefficient, because that won't mess you up. And now that we have all that, we're going to start the sketch. I start the sketch by plotting my zeros. So I have one at -4, one at 3, and one at -1. My end behavior, I'm going to be pointed down on both sides. And now I just need to figure out how to basically connect all those zeros together. So sometimes you might see where we just sort of have the pattern where we're sort of weaving through the zeros, but remember that you have to double check the multiplicity to see if you will be bouncing off at those zeros or whether you'll be crossing through the axis. So I'm actually going to go back to these zeros and I'm going to add in the multiplicity just right below. And I basically am considering how many times does each of these zeros occur. So if you see this term right here was being squared, that indicates we have a multiplicity of 2. So that 0 is occurring basically twice. It's called a double root. For this next one, there was no exponent, so that has a multiplicity of 1. And right here, we had a multiplicity of 3 because it was raised to the third power. Now, where this affects our graph is that with even multiplicity, you will be bouncing off your graph. So we have even multiplicity here at -4. So at my very first x-intercept, I'm going to be bouncing off instead of crossing through the x-axis. Now, my other two zeros have an odd multiplicity. So for those, I will be crossing through the axis. -1, it's going to look something like that. I have sort of had that like squiggly action going on because it had a multiplicity of 3. And then I am going to cut right through at 3 because that had a multiplicity of 1. And that is what my graph looks like. So now we're going to move on to the next example. And for this one, I'd like you to go ahead and pause the video and actually try to solve this one out. So look for the zeros, find the multiplicity, find all that information, and actually try graphing it yourself to see how prepared you really are and how well you get this. And then you can unpause the video to come back and keep watching and see if you got it right. All right, now that you've paused the video and done this yourself, I'm going to go over it. So first things first, we're going to find the zeros. Remember, I'm going to find 1 0 from each factor. So I have underlined my 3 factors. The first factor is just an x. So that indicates to me that my 0 will be 0. please don't forget to look at a factor that's just a monomial. It just has one term. Not every factor is going to be a set of parentheses with two terms in it. So if you have that x out in front, that's going to indicate that I have a 0 of 0. Okay? Because if I were to set that factor equal to 0, oh, x is equal to 0. Same thing will occur even if there is a coefficient and or an exponent out there, right? If it was 3x equals 0, x would still be equal to 0. If it was x squared equals 0, x would still be equal to 0. So if you have that monomial, that single term out in front that's just, it has an x in it, you will have a 0 of 0. And then finding my other two zeros is the same as the last time. So here I have a 0 of -5, right? Opposite sign of the positive 5 that's being added. I know that works because -5 plus 5 would equal 0. And then I'm just going to note real quick that that has a multiplicity of 2. Right? My first had a multiplicity of 1, so I honestly don't really care about that much, but this 0 has a multiplicity of 2. And then I look at my last factor. From here, I get a 0 of +4. And once again, we're going to have a multiplicity of 2, so I'm just going to go ahead and note that in advance. When I count up my degree here, I have 1x there, I have 2 here because it's squared, and I have 2 more here because it's squared. That gives me a total of 5, which is in fact an odd number. We have an odd degree here. When I look at my leading coefficient, there is no number being multiplied times x. So my leading coefficient is not actually written out. That indicates my leading coefficient is 1, which happens to be a positive number. So a positive leading coefficient. And what this all indicates to me is that I have this odd degree, so I know I'm going to have opposite end behavior. Since it's positive, that means I'm increasing. So I'm going to start at the bottom, and I'm going to have an increasing function. Thus, when I look at my left end behavior and my right end behavior, on the left side, I'm at the bottom, so my function is approaching negative infinity. And on the right side, I'm at the top, so my function is approaching infinity. Next, we're going to go label on the graph. So I have my zeros of 0. It's horrible. Oh, darn. Just clicked lots of things I didn't mean to. Well, I'm going to have to refill this in real quick. 0, 5, 2. Okay, so back to the zeros again. We have 1 at 0. We have 1 at -5. And we have 1 at 4. And with my end behavior, I know I'm going to be starting down here and ending up here. Now I go to connect, but I have to consider the multiplicity. So the first 0 I approach is -5. And over here, I'm reminded that I had multiplicity 2. So remember that when you find the zeros here, that is not the order that you're necessarily going to come across them on the graph, right? On the graph, you're going to hit -5 and then 0 and then +4. So definitely consider the multiplicity that goes with the actual value where you're going to be crossing the graph. But so at 5, I have multiplicity 2. So as I approach this first 0, I'm going to bounce off the x-axis. Then I'm going to go back for my next 0, and that is at 0. I see here I had a multiplicity of 1, so I can cross right on through. And then my next 0, I'm going to have to come back down and approach is 4, and I saw multiplicity 2 again. So there is a bounce, and my function looks something like this. The next skill that we're going to review is division of polynomials. So I'm going to go ahead and solve this division problem in 2 ways. First in long division, second in the area model. So if you're an area model fan and you don't want to be using long division on your quiz, you can feel free to skip this slide and go to the next slide and do that with the area model if you prefer. I will go over both examples. If you're a long division fan, feel free to pay attention here. So as I set up my long division, I take my dividend. I'm going to write that out under my long division symbol, and I will take the divisor and write that on the outside. And then remember we have this pattern where you basically factor, multiply, subtract, factor, multiply, subtract. So the first thing I'm going to do is try to figure out how many times x fits into x squared, right? How many times does x fit into x squared? And that is going to fit in x times, since x times x gives me x squared. So I'm going to put an x up here. I'll then multiply it times the x and times the 5, giving me x squared plus 5x. And then I go ahead and subtract. I'm going to put this in parentheses to subtract both terms. So x squared minus x squared is 0. 3x minus 5x gives me negative 2x. And then I go ahead and bring down the negative 10. And then I start this pattern again. I'm looking to factor, multiply, subtract. So how many times does x fit into negative 2x? Basically, what do I have to multiply x by to get negative 2x? Since the x is already there, all I'm going to have to do is multiply by negative 2. So I'm going to multiply negative 2 times x to get negative 2x, multiply negative 2 times 5 to get negative 10. Go ahead and subtract. Negative 2x minus negative 2x is 0, and negative 10 minus negative 10 is also 0, because minus a negative is the same thing as adding. So if you want to sort of do that and it helps you to write the operations like that, you can do that as well. But since we found 0 down here, that is my remainder. So if I don't have a remainder, my problem is over. I don't have to worry about writing the remainder, and my solution is x minus 2. Looking here at the area model for division, I'm going to go ahead and have to set up my box. So I know my box will have the same number of rows as terms in the divisor. So I know there's 2 rows, one is x and one is 5. Now, to figure out how many vertical lines I have to draw, I need to know the difference in degrees. So you'll see a degree of 2 and a degree of 1. Since the difference of those, aka the subtraction, since 2 minus 1 is 1, I'm going to draw one vertical line, and then I can go ahead and label around the edges of my box with the numerator. So x squared plus 3x minus 10. When it comes to actually filling in this box, first thing is to copy this term in right here. Then I'm factoring, so what do I multiply x by to get x squared? I multiply it by an x. Then I multiply the x and the 5 together to be 5x here. Again, I do that because the label of the column and row will multiply to the term inside the box. The next thing I do is I take 3x and I subtract 5x to get negative 2x here. And the reason for that is because that diagonal right there with these two terms in it, that diagonal needs to add to this out here. And at this point, I have factored, multiplied, subtracted, so I'm good to go and start the cycle again. I need to figure out what do I multiply x by to get to negative 2x. Multiply that by negative 2. And multiply negative 2 times 10. Sorry, negative 2 times 5 to get negative 10. And I'm all done. You'll notice that this negative 10 matches what is in here. That means that I have a remainder of 0, so there is nothing else to go with my answer. And my final answer is x minus 2. Okay. And again, just as a brief reminder, if you're trying to find the remainder from this, let's say that this wasn't 10, all you do to find the remainder is take this number and subtract whatever is in here. Right? So in this case, it was negative 10 minus negative 10. That's why it gave us 0. Right? But if that was some other number, by taking this and subtracting this, that is how you get your remainder. Moving on here, we have the remainder theorem. So our question here is, what is the remainder in the division below? So I just explained in that last area model problem how I find the remainder in a division problem. However, there is a shortcut if you don't want to have to perform out the whole division and all you're being asked is about the remainder. So, man, why does this keep skipping around? Okay. And the shortcut is by using the remainder theorem. So we've learned that if you divide a polynomial f of x, so polynomial, aka that's going to be this fella. I'm dividing a polynomial by x minus c. So that's going to be this fella, right? This is f of x over x minus c. The remainder is going to be f of c. Right? So the remainder of this division is just whatever number was right there, plugged into my function. So I have to identify what c is. If x plus 3 is being represented as x minus c, then my c value is going to be -3. Two ways to think about this. In class, we learned you can actually solve this to solve for c. You could subtract x from both sides, they'll go away, and you would find that 3 equals -c. I can divide both sides by -1, and I would find that -3 is equal to c, meaning I want to find f of -3. Now, your other option, the option that I recommend and think probably makes more sense, or is at least a little bit faster, is to just rewrite the denominator as a subtraction. So the denominator was already a subtraction, right? If it was just like x minus 5, you would already have your c value. It would just be 5. But if it's not written as a subtraction, I'm going to rewrite it as a subtraction so that I can find c. And I'm just going to write x plus 3 as x minus -3. Minus a negative is the same as an addition. So I can rewrite the addition as minus a negative. But now that I have this and I needed it to be x minus c, my c is whatever I'm subtracting, so I'm subtracting -3. And just like with the other method, that shows that I need to be finding f of -3. And when I find f of -3, that will give me my remainder. So I'm going to go ahead and plug -3 into my function. So instead of writing 3x to the fourth, I'm going to write 3 times -3 to the fourth. Instead of -8x squared, I'm going to write -8 times -3 squared. I'll write plus 7 times -3, and then -4. And we are going to take that, and we are going to go ahead and write that, type it into our calculator, and double check to see what that is equal to. So I can't actually keep showing this when I go to my calculator, so I apologize for that. But I'm going to type this as it was. So 3 times -3 to the fourth. Press my little arrow over, so I'm not in the exponent anymore. Then -8 times -3 squared. Press my little arrow, so I'm not in the exponent anymore. Plus 7 times -3 minus 4. You'll see it gives me this answer of 146. Now, little refresh, I know I emphasized this in class. Please make sure you're using a calculator where you can actually see all your work at once. That will basically be an indication that you're using a calculator that knows how to follow the order of operations. Please don't just use your iPhone calculator or some other random four-function calculator where you have to press equal after each operation. You should be able to type out the whole expression as one and then press equal in order for it to give you your answer like this. I recommend Desmos. Anyways, we just found that f of -3 was equal to 146. So when I am asked what is the remainder in the division below, my remainder would be 146 because your remainder is always going to be equal to f of c. Right, now I would like you all to take an attempt at this. So here we have the same function, the same f of x, but a different denominator. So I would like you to write the denominator as x minus c, determine your c value, and then try out this example. Go ahead and pause the video, and when you're done, you can unpause it and I will go over it. Okay, so in this example, when I rewrite my denominator as a subtraction, that would be x minus -1. What that indicates to me is -1, that's the number that I am subtracting, so that is my c. That means that in order to determine the remainder, I'm going to find f of -1. So I have 3 times -1 to the fourth minus 8 times -1 squared plus 7 times -1 minus 4. Oh, darn. Big whoops there. Okay. Now that I have that, again, you can type in a calculator. I'm actually going to do this one by hand just because I think it's a little bit easier if it's a number like -1. Right, you have 3 times 1, which is 3. You have -8 times 1. You have 7 times -1, -4. 3 times 1 is 3, -8 is -5, -7, -4, and this is all going to come out to -16. Obviously, you can type that in the calculator if you prefer that. I was just going to show both ways. But since f of -1 is equal to -16, your remainder in this division problem would be -16. Last type of problem we are going to go through. So here, consider the polynomial f of x equals x cubed minus 2x squared minus 5x minus 12. So we did this in class, but I just wanted to go through it again to show you the thinking here and how this is the type of problem that really combines all of the other learning that we've done. So the first thing it asks us to do is verify that f of 4 equals 0. So what you would do is you find f of 4. And f of 4 is just, I'm going to be plugging in 4 instead of all my x's. So 4 cubed minus 2 times 4 squared minus 5 times 4 minus 12. Again, you're then going to go into a calculator, type this out, double check. Again, my annotations aren't going to carry over, so I apologize, but I just have it. I took a picture of it. And I was asked to verify that it equaled 0. When I typed it in the calculator, it did equal 0. So that equals 0. Check that. Now, if you were asked to show your work for something like this and I do not see this and you just say that f of 4 equals 0, then that is not going to gain you credit because I need to actually see that you're verifying it, right? Not just assuming that it's correct because the problem tells you. So this is how I verify, is by actually plugging the 4 in. After that, we're told since f of 4 equals 0, right? We just verified that. Since that's true, what must x be divisible by? Well, if f of 4 equals 0, right, we plugged 4 in as my x, and that gave me a 0. That means that one of my zeros is 4, right? When x is 4, my function is at 0. So that indicates that my function must be divisible by x minus 4. This is the reverse of what we did when we were graphing, where when we were graphing, you would have been given a factor that said x minus 4, and you had to say like, oh, I know that my 0 is 4. Here you're given the 0, 4, and you're just asked to go backwards. It's the same idea where you're going to have the opposite sign, right, is going to be the number that you subtract after x. So since my 0 was positive 4, I subtract 4 from x. Next, it asked me to use polynomial division try to factorization of f of x. So how do I do that? Well, if my function is divisible by x minus 4, right? If x minus 4 is one of my factors, that means that if I divide my function by that, I will be left with the other factor. So I'm going to take my function and I'm going to divide it by x minus 4. Now, you could do this with either method you prefer. You could do it with the area model or you could do it with long division. I'm going to do it with long division because I prefer that and I think more of you guys prefer that. But if you want to use the area model, that is a-okay. But as I go ahead and divide it, x fits into x cubed, x squared times. Multiplying x squared times x, I get x to the third. X squared times -4, I get -4x squared. Subtract both of those, and I'm left with 2x squared. Bring down the minus 5x, and I start my process over again. How many times does x fit into 2x squared? Well, that fits in 2x times. 2x times x gives me 2x squared. 2x times -4 gives me minus 8x. And then I'm going to subtract -5x minus -8 gives me positive 3x. Then I bring down the -12. I say how many times does x fit into 3x? That happens positive 3 times. 3 times x gives me 3x. 3 times negative 4 gives me negative 12. I go ahead and subtract. 3x minus 3x is 0. Negative 12 minus negative 12 is also 0. So my remainder is 0. And when I divide by x minus 4, I'm left with x squared plus 2x plus 3. Okay. That tells me that if I'm writing this factorization, if I have to write it in factored form, which I was asked, so I need to write it out in factored form, then I had my first original factor of x minus 4, and I used that to find the other factor of x squared plus 2x plus 3. From there, I'm asked to find the remaining solutions to the equation f of x. So I already found the solution from x minus 4, right? I found that x equals 4 is a solution there. So I don't need to worry about that factor, but I'm going to find the solutions to this other factor. So what numbers would make x squared plus 2x plus 3 equal to 0? Well, I'm going to have to solve this through the quadratic formula. The reason for that is because I can't use factoring to solve because it does not factor. I cannot use the square root method to solve because I have an x squared and an x. So I'm going to use the Pythagorean theorem. Sorry, not the Pythagorean theorem. I teach geometry too. I'm going to use the quadratic formula. For the quadratic formula, the coefficient of your x squared is your a value. Since there's nothing written there, my a value is 1. Your b value is the coefficient of x, which here is 2. And your c value is your constant. Here it is 3. Now, the actual Pythagorean theorem, I'm going to have to write this up here, so I apologize. I'm going to erase some of this stuff. But the quadratic formula, did I say Pythagorean theorem again? I don't know. The quadratic formula states negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm just going to plug a, b, and c into that formula and then go ahead and simplify until I have my result. So negative b is negative 2 plus or minus b squared is going to be 2 squared minus 4ac, so minus 4 times my a is 1 times my c is 3 all over 2a, so 2 times 1. And if you recall back from our quadratics unit, you're going to have to simplify the 3 parts separately, so negative 2 can't be simplified. I'm going to do 2 squared minus 4 times 1 times 3 in my calculator. You could type that all in, or you can do it by hand. That comes out to 4 minus 12, or in other words, negative 8. And again, you're only simplifying the part under the radical. If you type the radical in with it, it's not going to give you an answer in a calculator, so please don't do that. Simplify specifically what is under the radical. And then you're left with negative 2 plus or minus square root of negative 8 over 2. The last step is to simplify this because right now you have the square root of a negative number, and we never leave things as the square root of a negative number because technically you can't take the square root of a negative number. We're going to rewrite this as a complex number by using I, our imaginary number, to represent the negative part of the root. So since I represents the negative part of a square root, it's equivalent to root negative 1. I rewrite this as negative 2 plus or minus I root 8 over 2. Okay? And there you go. There is an answer. Technically, that is not as simplified as it gets. So if you are someone who is like, this is a little easy, I need myself a challenge, you could go ahead and simplify this further, right? When we talked about simplifying radicals, we talked about rewriting a radical as the product of two numbers where one is a perfect square. So I could absolutely say that the square root of 8 equals the square root of 4 times 2, and then rewrite it as 2 root 2. So if you wanted to go through, you could find that. Right, negative 2 plus or minus 2i root 2 over 2. And from there, you could even simplify it further because every term has a 2. So if you basically factored a 2 out of all of them, divided, it would become negative 1 plus or minus I root 2. So that is equivalent to this. You are welcome to stop here for the purposes of these problems, but I just wanted to show that in case you were ready for a challenge. With that being said, this is the end of the video. So if you didn't understand any of that, please, please, please reach out to me prior to the start of the quiz. After the quiz starts, please don't come to me telling me you don't understand. It's too late at that point. But come to me prior, ask me a question. I can try to help you out. But yeah, other than that, good luck studying. Make sure that you go ahead and do some review on your own. Again, you should have done these problems from the video along with me. If you didn't, maybe go back now and try to do it again. Try to look at some examples from class and just redo things from your notes, but actually practice writing out and solving the problems, not just looking at it solved out, because practicing actually solving it out is what's going to make you more confident, be able to work through it quicker and stuff like that. So yeah, questions, let me know. Other than that, good luck and have fun on the quiz.